So today we're going to look at the cubed root of 1, the roots of the cubed root of 1. So we've got the cubed root of 1 equals something. Now the first thing I'm going to do is cube both sides and have x cubed equals 1. Then I'm going to take x cubed minus 1 equals 0. Then I'm going to put that 1 as a cubed entity, so I can use the difference of cubes now to factorise this. They either both have to be equal to 0 or one of them has to be equal to 0. So to solve this part, I just say, I'll come up here, I'll say x minus 1 equals 0, so x equals 1. So that's one of the solutions. Okay, x equals 1 is a solution. But there's other solutions, because I need to look at this bit, this quadratic part of the equation here. So I can solve that using the quadratic formula. So x squared plus x plus 1 equals 0. I've got my a, b and c quantities are all equal to 1. So I can just bang that straight in the quadratic formula. So minus b is minus 1 plus or minus the square root of b squared. That's 1 squared is 1 minus 4 times a times c all divided by 2a is 2. So I basically just have to solve this then. So I get minus 1 plus or minus 1 minus 4 is the square root of minus 3 over 2. And I'm going to get two solutions here. I'm going to get minus 1 over 2 plus root 3 over 2i. Yeah, and minus a half minus root 3 over 2i. So these are my two complex solutions, so I need to put them in here. So I've got x equals 1 or x equals minus a half plus root 3 over 2i, or x equals minus a half minus root 3 over 2i. And these are my three solutions to the cube roots of unity. Now you'll notice one of my solutions is real, it's just 1, and the other two solutions are complex solutions. Now there's another way to think about this. If I draw an Argand diagram with a real and imaginary axis, and I put my first solution, x equals 1 there, what I can do is split, if I imagine, because this is 1 up here, I can imagine a circle with a radius of 1. Now, because I will need three solutions, I can divide the circle into 3. I can come 120 degrees that way, or 2 pi over 3 radians, and then come another 2 pi over 3 radians that way. And these are the three solutions to the cubed root of 1. So you can see one of the values is purely real, but the other two are complex. So how would I figure out what they are? By geometry, or by like the graphical method? Well, I'd have to use the modulus argument form of complex numbers. So let's look at the first solution. Well, first, the modulus form of a complex number is r cos theta plus I sin theta. Alright, well my r is 1. Yeah, that's the modulus of these 3 points. So r is just 1. So the first solution, I'll call it z1. That's just 1, so I can just leave it out. It's going to be cos this angle here, 0 degrees, 0 plus I sin 0. Well, the cosine of 0 is 1, and the sine of 0 is nothing, so that's nothing goes there. So the first solution is z1 equals 1, which is the purely real answer we got there. Now the second solution, I'll call it z2, where it's going to be cos 2 pi over 3 plus I sine 2 pi over 3. Now if you bang these in your calculators, you'll need your calculator set to radians, and the cosine of 2 pi over 3 or 120 degrees is going to be minus a half. Yeah, and the sine of 2 pi over 3 is root 3 over 2. And this is the first complex root, which you'll see is the same as that one there. And the final one then, Z3 for completeness, equals cosine minus 2 pi over 3 plus I sine minus 2 pi over 3. And the cosine of minus 2 pi over 3 is minus a half. And the sine of minus 2 pi over 3 is minus root 3 over 2i. And you'll see, so this first solution marries up to that one. The second one there marries up to that one there. And the third one is the same as that one here. So we had two methods to do the same thing. Up here, I did it algebraically, and then down here, I've done it graphically using the Argand diagram and the modulus argument form of complex numbers. Okay, I hope you enjoyed that. I'll see you later.